So we just found out that the first coefficient of any power series is not just random. The first coefficient of our power series tells us the value of the function when x equals a. So if I have a power series in just x, the first coefficient is what I get when x equals 0. If my power series is centered at 7, I'd have coefficient times x minus 7 to the power n, and I'd have one of those for every whole number n. Well, I can use that same idea with the derivative of the function. The derivative of a power series has different coefficients than the function I started with, but their formulas are very simple based on the coefficients that I started with. So my derivative of the power series starts off with coefficient C1, which used to be the coefficient of the linear term on my original power series. Here it is. Then I've got twice the C2 coefficient, and C2 used to be the coefficient of the quadratic term. Here it's multiplied by x minus a. Then I've got 3 times the coefficient that used to be on the cubic term, and here it's on the x minus a squared, and so on. So my first derivative of the power series, evaluated at x equals a, gives me the C1 coefficient from the original power series. Now, I can keep doing this because I know that as long as a power series is convergent, right? As long as I'm looking in that narrow window where the power series actually gives me a function I can compute, then it's going to have a derivative. Its derivative is also a power series. And I could take another derivative. I could take a second derivative. That second derivative is also going to be a power series. Its formula is given right here, at number 3. So the second derivative of the power series is going to start with coefficient twice C2. Then 2 times 3 times C3 times x minus a, and so on. Where did these numbers come from? I've used the power rule for differentiation twice. Well, that means that the second derivative of the power series, evaluated at x equals a, is twice the coefficient C2. So the first coefficient is telling me information about the C1 coefficient is telling me information about the first derivative of the function, whether or not that function is increasing or decreasing. The second derivative is recorded in the C2 coefficient, whether the function is concave up or concave down. Be remembering all of these things from differential calculus. The better we understand a function's derivatives, the better we understand the function itself. So let's keep going. Let's take a third derivative, which is obscured under there. F triple prime of x has the following formula. We've got 2 times 3 times the coefficient C3. We've got 2 times 3 times 4 times the coefficient C4 times x minus a. We've got 3 times 4 times 5 times the coefficient C5 times x minus a squared. So what have I got here? The third derivative evaluated at x equals a is going to equal 2 times 3 times the coefficient C3, which is 3 factorial times C3. So remember, factorial is 1 times 2 times 3, and we stop at whatever whole number we're taking a factorial of. And here we've just dropped the 1 because 1 times anything is itself. The pattern that we get is that the nth derivative of the power series evaluated at A is equal to n factorial times the nth coefficient, C sub n.